doing heat, chapter 14, the last chapter of Physics 2143. The title of the chapter is heat, but I think really we need to think about three different terms, and if you understand these three terms, it all becomes pretty obvious. When you heat something, what happens? Well, it gets hot. So heat is somehow related to temperature, and you know it's also related to energy, because if I want to heat something up, it takes energy. So what's the connection between heat, energy, and temperature? Well, it's this. Materials have what's called thermal energy, and thermal energy is just the random motion of the particles. So as you heat something up, as you increase the energy, the particles race around, but also they can vibrate and rotate and move in different ways. So heat is the transfer of thermal energy. What's temperature then? How is temperature related to this? Temperature is a measurement of one specific aspect of the thermal energy, of the average translational kinetic energy. We've talked about kinetic energy. There's rotational kinetic energy and translational kinetic energy. So if I heat a gas up, the temperature increases as the molecules start speeding around. But as I put energy into the gas, something else happens. If it's a diatomic molecule such as H2, the two hydrogen atoms, they can start spinning around like that, and that takes energy. So the thermal energy is the sum of all of the energy. The temperature is a measurement of the translational kinetic energy, the average translation of kinetic energy, and heat then is the transfer of energy. It's the thermal energy in motion, if you like. Okay, so try and keep those ideas in the back of your mind. There's a nice picture of some people camping here. I guess the idea is that we have a heat source and they're feeling warm, so that's heat transfer by radiation. And then if you put your hand above the fire, it would also be warm because we have convection. The fire is heating the air, the hot air is rising, so that's called natural convection. And then I guess the sausages that they're cooking, don't know if you can see the sausages, but they're being heated on the outside, and then conduction causes the sausages to heat up on the inside. So you have all three heat transfer mechanisms going on in the picture. Okay, there's the contents. Let's start at this slide here. We often speak of heat as though it were a material that flows from one object to another. It is not, rather it is a form of energy. Back in the 18th century, they thought that heat was a fluid. I don't know if you remember, but when we were talking about charge, in the 18th century, that also was thought as a fluid. So in the 18th century, there was an idea that, we have fluids, and if the fluids are out of balance, then things slosh around. So that's where the idea of positive and negative came up with electrical charge. Either you have too much electrical fluid or too little electrical fluid. And they had a similar idea with heat, and the heat fluid was called caloric. And they thought, well, if something's hot, it's got too much heat fluid and it flows to something cold, which sort of makes sense, doesn't it, right? You can imagine this heat fluid flowing from hot to cold. Anyway, that isn't right, but the name caloric gives us this name here, the unit of heat, calorie. But that's a bit odd, isn't it? Because we've talked about energy, and in SI units, we know that the unit of energy is the joule. And so it says here that it is a form of energy, so why don't we have the joule there? Well, the reason is because this unit here, the calorie, is defined in terms of heating of water. So the definition of a calorie, now we have to be a bit careful here, this is a little c here, this is a physics calorie. A calorie is the amount of heat necessary to raise the temperature of 1 gram of water by 1 Celsius degree. Right, so it's a unit of energy, but just like the electron volt is a unit of energy, the joule is a unit of energy, the calorie is also a unit of energy. And when we're considering heating things up, this is a good unit to use. It's very handy because it's defined in terms of heating things up. A food calorie, which is spelt with a big C, I don't know if they've got it here, but if you have a food calorie, you'd write it with a big C. It's actually a kilocalorie. So a food calorie would heat 1 kilogram of water by 1 Celsius degree. There is a the BTU, which is a British thermal unit. That's sort of the British equivalent of the calorie, and a British thermal unit is the amount of energy required to heat 1 pound of water by 1 degree Fahrenheit. And if you ever buy a barbecue or a gas heater for your house, they're often rated in BTUs. It's a bit of a lie, really, because the barbecue, if it's a 50,000 BTU barbecue, that's actually 50,000 BTUs per hour, right? Because you actually want the power of the barbecue, not the amount of heat it puts out, okay? The rate at which it can deliver the energy. So BTU is another unit, but we don't worry too much about BTU, okay? James Joule. Why is James Joule famous? Mainly for this experiment here. And it's one of those things, when you think, you look back and say, why didn't they realize this? Why did it take so long for them to figure it out? But this is Joule's experiment. And in Joule's experiment, he had a falling mass. And you can imagine that this mass is losing potential energy. We know it's mgh. And as the mass falls, it turned these paddles in water. So the mass fell slowly because it was having to turn these paddles around in the water. And Joule sort of dropped this weight from a certain height. He measured the temperature before it dropped, the temperature after it dropped, and found that it heated up. And he said, aha, there's a connection between mechanical energy and heat energy. And so this thing here, this is known as the mechanical equivalent of heat, right? 4.186 joules is equal to 1 calorie. Okay, so that's what James Joule sort of found out and what he was famous for. He made a connection that heat was just a form of mechanical, is another form of energy. I guess the difference is that heat is a very unordered form of energy, whereas mechanical energy is very ordered. So that's getting into the world of entropy, which we won't really get into too much. Okay. So that's the what's called the mechanical equivalent of energy. So definition of heat then. Heat is the energy transferred from one object to another because of a difference in temperature. Okay. So usually in class I get people to run around, and someone running fast bumps into someone who's running around slowly. Well, the person running around fast has a high temperature because we said that the temperature corresponds to the translational kinetic energy. What happens when someone running fast bumps into someone running slowly? Well, the fast person loses energy and the slow person gains energy. So what's happened is that the energy has been transferred from hot to cold. So naturally, because of collisions, the heat transfers from hot to cold, right? And so heat then is the energy transferred from a hot object to a cold object. Remember that the temperature of a gas is a measure of the kinetic energy of its molecules. Okay, the sum total of all the energy of the molecules in a substance is its internal or thermal energy. I tend to use thermal energy, right? So that's the total energy. And remember what I said at the beginning, it's not only the translational kinetic energy, the molecules can be vibrating and rotating around, doing all sorts of other things, right? So there's many ways in which a material can sort of hide this energy other than just whizzing around, okay? So the internal energy is the total energy of all the molecules. Heat is a transfer of energy due to a difference in temperature. Now, we won't get into gases too much because we didn't really do the chapter. We needed to have done the chapter before this to do gases. But, I mean, there's one idea we can take away from here. Internal energy of an ideal atomic gas is equal to the average kinetic energy per molecule multiplied by the number of molecules. Now, an ideal atomic gas will be like helium. It's just an atom. And the only way that helium can store energy is by running around. Internal energy of an ideal atomic gas. This is for an ideal atomic gas. Again, we haven't really covered this. Let's not worry about this, but I think on the next slide, right. So you can imagine helium goes around as a single atom. That has energy just due to racing around. But if we consider something like nitrogen or hydrogen, which goes around as H2, you can see that these gases, as well as running around, they can spin around or they can vibrate. So if the gas is molecular, the internal energy is not only due to them racing around, but we have to add another term because they can vibrate and rotate. Now, this will become important in a little bit later when we look at what's called specific heat capacitors. And here we go, specific heat capacitors. And again, we're not going to worry about gases in the course too much. We're going to worry more about sort of liquids and solids. So the specific heat capacity tells me how much energy I need to heat up a unit mass of the material by 1 degree centigrade. So you can see that the units of specific heat capacity is how many joules I need to heat a kilogram by 1 degree centigrade. Instead of using joules, of course, what I could use is kilocalories per kilogram degree centigrade, which is equal to calories per gram degree centigrade. Now, if you think about how the calorie was defined, the calorie was defined as the heat required to heat 1 gram of water by 1 degree centigrade. So, given that, what's the specific heat capacity of water? 1. Let's have a look. Water. 1. There it is. Because it takes 1 calorie to heat 1 gram of water by 1 degree centigrade. That's how the calorie was defined. So you can see it's sort of a good unit for when we look at heat. The calorie is a sensible unit to use. It sort of makes sense that the specific heat capacity of water is 4186. That number there, 4186, if we go back a few slides, you might recall that we saw that number there before. And so it sort of makes sense that it takes 4,186 joules of energy to heat 1 kilogram of water by 1 degree centigrade, if you think what the calorie is, right, and how the calorie is defined. The amount of heat then to effect a change, the amount of heat, Q, is equal to the mass of the amount of material being heated multiplied by its specific heat capacity multiplied by the temperature change, okay? So that sort of makes sense dimensionally because I've got joules per kilogram per degree centigrade times kilograms times degree centigrade, right? So this is telling me how much heat I need to heat a given mass by a given temperature, and C is the material called the specific heat capacity. So the specific heat capacity is an intrinsic property of the material. So you know, it's a bit like resistivity. We could talk about the resistance of a piece of copper, but copper itself has a resistivity. So materials themselves have a certain resistivity. If we look here, let's see, a low number like lead, if we look at lead, 130, that means it doesn't take much energy to heat lead up, right? 130 joules to heat a kilogram of lead by 1 degree centigrade. If we contrast that with water, when we look at water, for example, here, 4186, you can see water, it takes a lot of energy to heat water up, doesn't it, right? 4,186 joules to heat a kilogram by 1 degree centigrade compared with lead, which is 130. Why the difference? Well, when I was talking about the gas here, that's why I was emphasizing this point. The water molecule is a complex molecule. It's got oxygen, 2 hydrogens, and the water molecule can vibrate and rotate in many different modes. So when I put thermal energy into water, a lot of that energy goes into making it vibrate and rotate, and not so much of it goes into making it translate. When I heat lead up though, the electrons whiz around faster and faster. It's easy to heat up. Generally, you'll notice that all of the metals heat up pretty easy, right? It doesn't take much energy to heat metals up. We're just making the electrons move faster, and they can't vibrate and rotate in all of these complex ways. This actually means that our water then is very good at storing thermal energy, and this is why when you think about the seasons, winter starts on the shortest day of the year because the oceans keep the climate warm, and only come the shortest day of the year does it start getting colder. And the same in the summer. On the first day of summer, the days start getting shorter, but that's the first day. But by then, the oceans in the northern hemisphere have heated up, and we tend to get the warmer weather then. You can imagine there's sort of a phase lag between how the sun's heating the earth and what the climate's doing. The climate sort of lags behind because the oceans take a long time to heat up and a long time to cool down because they store a lot of thermal energy. This is the specific heats of gases. I'm going to skip this because, again, we haven't really looked at gases. This goes back to a previous chapter which we didn't really care about. So we'll skip that one there. Calorimetry, well, the metry ending means to measure. Calor is heat. So calorimetry is the science of measuring heat flows. A calorimeter is a very simple device. It's just an isolated system. So let's say a polystyrene cup would make a good calorimeter. So what I could do, I could get a polystyrene cup, I could put some water in it, I measure the temperature, I get a hot piece of metal, I put it in the cup, I let things come to a final temperature, and I measure the final temperature, and then I could work out the specific heat capacity of the metal. How could I do that? Well, I know the initial temperature of the water, I know the final temperature of the water, so I know how much energy has flowed into the water. Where did that energy come from? Well, it came out of the metal. And if I know the initial temperature of the metal and the final temperature of the metal and the mass of the metal, I should be able to work out the specific heat capacity of the metal. So there's a few problems like that on the worksheet, and we'll go through some. But that's a basic idea of a calorimeter for an isolated system. The energy out of one part equals the energy into another part. Heat loss equals heat gain, or the sum of Q equals 0. If we go back here, you can imagine Q always indicates heat flow. If I add up all of the various heat flows in a calorimeter, it's equal to 0 because we have no heat coming in or out of the system. So here's a calorimeter. It's a very simple device. We probably have water in it. We have a thermometer, and it's just very well insulated. If I was to do an experiment here, maybe I'll drop a hot piece of metal in. The water would heat up. So would the calorimeter cup. So I'd have to take that into account. But I could work out the specific heat capacity of the metal, or whatever the one unknown was. Okay. So that's your basic calorimeter. There's another type of calorimeter, and the other type of calorimeter is called a bomb calorimeter, and this is how you measure the energy content of food. And basically you have the food sample surrounded by water, and you burn the food. You literally burn the food in oxygen, and it heats the water up, and that gives you the energy content of the food. The only trouble with this is it gives you the energy content of the food if you burn it in oxygen. Your body does not burn food in pure oxygen, so it can be a little bit misleading. Of course, oils have a high energy content. Oil burns very well in oxygen, produces a lot of heat. Your body's metabolism, though, acts in a different way, so it can be a bit misguided. But that said, lay off the potato chips. This is an important diagram, and usually I want you to be able to sketch this, okay? So we know that when we heat water up, at some point it starts boiling and the temperature doesn't change, okay? So what this plot here is showing, and this is an important one, this is ice at 0 degrees centigrade, and this is heat added, right? This is ice at minus 40 degrees centigrade, here's 0. So as I put energy into ice, what happens? It heats up. So the slope of this is related to the specific heat capacity of ice. I put energy in, ice heats up. But then the ice gets to 0 degrees centigrade and it stops heating up. Instead, it melts, and it melts at a constant temperature of 0 degrees centigrade. Where is the energy going? Right? I'm putting energy in, but it's not getting any hotter. So this is called latent heat. The word latent means hidden. Okay, so we call this latent heat because I put this much energy in and the temperature hasn't changed. Well, what has changed is the state, right? It's the ice has gone from a solid to a liquid, and it took energy to break those bonds apart, right? So I start with ice at minus 40, I put energy in, the ice warms up, I then have to put this much energy in, and that it changes from ice at 0 degrees centigrade to water at 0 degrees centigrade. Now, if I continue to put energy in, what happens to the water? Well, the water heats up. I put energy in, the water gets hotter. But that keeps happening up till this point here, at 100 degrees centigrade. Now, at 100 degrees centigrade, the water starts boiling. And when the water starts boiling, it doesn't get any hotter. But again, what am I doing? This energy that's going in is causing the liquid to turn to a gas, right? So that energy, it's hidden, it's there, but it's hidden away because it's going to changing the state from a liquid to a gas. So I put this much energy in, and then the water at 100 degrees centigrade turns to steam at 100 degrees centigrade. Once I've done that, I continue to put energy in, I start heating the steam up. Of course, the interesting thing here is we can come backwards. If I have steam here at 100 degrees centigrade, if I condense the steam out, I get this much energy. Look at the red bit. I get that much energy coming out of it. How much energy does it take to heat water up from 0 to boiling? It takes that much energy. How much energy does it take to do I get when I condense steam? I get that much energy. So the next time you're buying one of those expensive coffees from Starbucks and they go shh, shh, and put steam into it, think about what's happening. They're condensing the steam out, and as the steam condenses out, all of this energy is released. So the cold water or cold milk takes can easily be heated by the steam. The same if you have a drink, if you're having a nice drink while you're watching this, you put ice cubes into it because the ice starts at 0 degrees, and to melt the ice, it absorbs all of this energy, right? So you put ice at 0 degrees in, and it takes a lot of energy to melt the ice. So the ice can really cool the drink down. If you put water at 0 degrees centigrade into your drink, it isn't not really going to work very well. You need ice, because ice needs a lot of energy to change the state. Okay, so this is sort of an important diagram here. So try and sort of be able to sketch this diagram. So this is the values for the latent heat, or what's called the latent heat of fusion and vaporization. Okay, so this tells me how many kilojoules I need to melt a kilogram of the material. So if we look at water here, you can see we need 333 kilojoules of energy to melt 1 kilogram of ice. Vaporization, if we look at water, it takes 2,260 kilojoules of energy to turn 1 kilogram of water from a liquid to a gas. Okay. What else is there to say here? We've got the melting points. Okay. But again, the important point here, if we look at this graph here, I'm going to go back to emphasize this. What that is really telling us then, what that graph was telling us is the size of these things here, right? How much energy it takes, okay? So for a phase change, when we have a phase change, the amount of heat is mL. If we go back, if you think about the specific heat capacity, it's the mass times the specific heat capacity times a change in temperature. So this is a little bit different because we don't have a change in temperature when we change phase. So Q, the amount of heat to change phase, is just the mass times the latent heat of fusion or vaporization, depending on what's happening. So when we do a calorimetry problem, and there's one on the worksheet, what do we do? First, we ask, is the system isolated? Yes, it better be. And then we apply the conservation of energy. If there's no phase changes occurring, then the heat transfer will depend on the mass, specific heat, and temperature change. If there are phase changes, then we have to take those into account. So for example, if I got an ice cube, put an ice cube into some warm water, what heat transfer processes are happening? Well, the ice cube had to heat up from a negative temperature to 0. So that would be a specific heat capacity. Then the ice cube had to melt, which would be a sort of a latent heat of fusion term. And once the ice cube had melted, it would have to heat up to the final equilibrium temperature. Okay, so imagine an ice cube out of the freezer at -15 going into warm water. The ice cube heats up, that's one term. The ice cube melts, it's a second term. And then the ice cube heats up to the final temperature of the water, that's a third term. I know the initial temperature of the water, I know the final temperature of the water into which the ice cube was dropped. And so I could figure out all of these heat flows and figure out, well, one variable, the latent heat of fusion, for example, for ice. Okay, these problems, I have to say, when you do these calorimetry problems, we'll look at some, they're not complicated, but there's a lot of terms flying around in them, and you have to be a bit careful with the signs. So that's the thing about calorimetry problems. They just tend to be messy because there's lots and lots of terms all over the place. Let's think. Let's see. The latent heat of vaporization is relevant for evaporation as well as boiling. The heat of vaporization of water rises slightly as the temperature decreases. On a molecular level, the heat added during a change of state does not go to increase in the kinetic energy of individual molecules, but rather to break the close bonds. I think this is what I've essentially said already. Okay, heat transfer processes. There's 3 ways in which heat can transfer: conduction, convection, and radiation. This is conduction. We have a hot object, a cool object. We have some material connecting them, and you can imagine that the heat would flow from hot to cold down here. How fast does the heat flow? Well, Q over T, the rate at which heat flows, it's going to depend upon the area, right? The bigger the area, the more the heat can flow down. Also, it depends upon the temperature difference. I mean, if these are at the same temperature, no heat flow. But if I have a big difference in temperature, the heat's going to flow more quickly. So it depends upon the temperature difference. The length, if this is longer, right, the longer this is, the farther the heat has to flow, the slower it goes. So it's inversely proportional to L. And then it depends on the material, and K describes the material. This is known as the thermal conductivity. And hopefully, if you look at this equation, you can see it's a very intuitive equation. We have essentially the temperature gradient. You can think of this as, how steep it is, right? So T1 minus T2 over L, it's like the slope of the temperature gradient. If we have a steep temperature gradient, the heat can move fast. If we have a shallow temperature gradient, the heat moves slowly. So this is our equation for the heat flow. K, sometimes it's called lambda, is known as the thermal conductivity. And in the last lab that we do in the course, we actually measure the thermal conductivity of glass. So here's some thermal conductivities. So a high value of K means that a material is good at conducting. Now, when we looked at electrical conduction, we saw that metals were good at conducting electricity, and the reason was that they have free electrons. Well, these free electrons can also move the heat around. So what we see when we look at this table is that the good conductors, the good electrical conductors, are also good conductors of heat, right? So if you remember that these were the metals that were good at conducting electricity, steel was the one, and iron were not good at conducting electricity, and we can see that these are poorer, right? It's a practical point. If you have pots and pans, I guess the best one will be silver. Copper's good, aluminum's good, but steel or iron isn't so good, right? It's not a good conductor. So if you do own steel cookware or iron cookware, what tends to happen is you get hot spots on the bottom because the heat can't spread out sideways. So cast iron cookware is made to be very thick, so you get an even heat distribution on it. But often you'll buy pots and pans with copper bottoms on, because copper's a good conductor. The heat conducts sideways on the pan. Let's have a look. So we have silver, copper, aluminum. These are good conductors. And then things which are bad at conducting. Air is a terrible conductor. Fiberglass 0.048. Fiberglass we use to insulate houses, don't we? You put fiberglass bats in the wall. But that's kind of odd, because if you look at the conductivity of fiberglass, it's twice that of air. So wouldn't we be better off just putting air in the wall cavity instead of fiberglass? That's odd, isn't it? We put fiberglass in, but it's a better conductor of heat than air, so we'd be better off just putting air in. Strange that. If you think about all of these materials down here, which are good insulators, all of these things are good at trapping air. Polystyrene traps air, wool traps air, goose down traps air. Okay, the reason is fiberglass is better than air. Why is that? Well, fiberglass indeed is a better conductor than air, but there is another way which heat can move, and that's convection. So the point of having the fiberglass is it's a pretty darn good insulator anyway, but the reason we have fiberglass instead of air is because the fiberglass stops the air moving around. It stops convection, right? So convection is when heat moves around because a fluid, and remember fluid can be a liquid or a gas, just moves around. So if we had a wall, right, with just air in between it, the conduction through the wall would be very minimal. However, the one side, the inside would be warm, the outside would be cold, and what would happen is that the cold air would slump down and the warm air would come over and replace the cold air that had slumped down. And they would get a convective cell sort of set up within the wall. Okay. The point of double glazed windows, again, the point of double glazed windows is that it traps a layer of air and it stops the convection. So the piece of glass on the inside is warm, piece of glass on the outside is cold. The air is sort of trapped there in a very thin layer, and it can't really move around very much. And so that makes sort of double glazed windows very good insulators compared with single pane. When we talk about building materials, we talk about the thermal resistance, and you can see this is a bit like electrical stuff. The resistance is 1 over the conductivity times the length, the thickness of it. It's a bit of a weird unit because we need the area. So you can see that the resistance is it's a really weird unit, but the idea is that the resistance is per square foot, right? So these are weird BE units that they're using, but you have when you make a building, you talk about the thermal resistance. The resistance is related to the inverse of the conductivity times the length. We need an area, but they leave the area term out because then you can just multiply by the area of the wall to get the total resistance of the wall. So it's a bit of a weird way that they do it, and we needn't concern ourselves with it too much, other than if you ever do any building, you can buy R20 or R12. That's the thermal resistance. So it's very much like the electrical resistance that we talked about. Oh, we had a bit of a technical glitch. The phone ran out of storage space, so it's actually the next day. We were at convection and heat transfer mechanisms. We'd talked about conduction and now convection. So convection is when heat is transferred by the motion of a fluid. There are two types of fluids. Usually when I ask for the two types of fluids, people say beer and wine, but no, that's not the two types of fluid I'm thinking of. Fluids can either be a liquid or a gas. And so convection is when heat is transported through a liquid or a gas moving. There's two ways in which the liquid or gas can move. It can move in a natural way, or it can be forced. So this is an example of heat transfer by the natural convection of a liquid. The heat source down here is heating the water. This water, as it heats up, becomes less dense. It rises to the top, it loses heat, and then sinks back around. The next time you eat miso soup, take a look and you'll see this off circulation pattern. Again, this is a heat transfer by a liquid, and this is a hot water radiator system in a house. We have the furnace, which is the heat source, and the water transports the heat around the radiators, but in this case it's forced. We have a pump. So that would be an example of forced convection of a liquid. If we think of gases, an example of forced convection of a gas, well, that would be, for example, if this was like a Canadian furnace. Canadian houses tend to pump hot air around, or maybe even a hairdryer. A hairdryer has a red hot filament, and there's a fan that forces the air through that. So pumps force liquids and fans force gases. The one example we're missing is the natural convection of a gas. And I guess you could think this is an example. As this flame burns here, it heats the air and you can feel the air rising. If you ever have a convection heater at home, which are quite common, a baseboard heater or a convection heater it's called, you put your hand above an electrical convection heater and you can feel a warm air rising up. Again, the electrical element is heating the air becomes less dense and it rises up. So if you do have a baseboard heater, or sometimes they're called convection heater at home, that would be an example of the natural convection of heat by a gas. Let's see, this is just saying about the different types of heating. Our body temperature is regulated by the blood. It runs close to the surface of the skin and transfers heat. This is just about how humans regulate temperature. One thing that humans do very well is to be able to dump heat. So, when we consider other animals aren't very good at losing heat. Humans are very good. We sweat a lot, and the evaporation of the sweat allows the heat to escape. Okay, the third heat transfer method is radiation, and we can feel heat from the sun, but between us and the sun there's the vacuum of space. If you think about the other two heat transfer mechanisms, conduction and convection, these both require a material, so they wouldn't work in the case of a vacuum. And so we know about electromagnetic radiation. The electromagnetic radiation can travel through space. We're not going to look at this in detail, but there is this law here called the Stefan-Boltzmann law, which tells us that the power, Q over T, it's the power radiated by an object, is equal to the object's emissivity times a constant times the area times the temperature in Kelvin, the absolute temperature scale, to the fourth power. So you can see, for example, if I were to double the temperature of an object, then the power it radiated would increase by a factor of 2 to the 4, which is 16. This constant here is called the Stefan-Boltzmann constant, and emissivity tells us how well an object radiates. E is between 0 and 1. A black object is very good at radiating. A silvered object is very bad at radiating. Basically, if an object is good at absorbing radiation, it has to be good at emitting radiation. You can imagine if I have an object, for example, this Futurama CD here, if it's in the room, it's radiating energy out. Why doesn't it just get really cold? Well, because it's also absorbing radiation. But what if I could make it better at emitting than absorbing radiation? well then it would be colder than the room around it. But we know that doesn't happen. If I leave this CD in the room, DVD, sorry, not a CD, if I leave this DVD in the room overnight, it comes to the ambient temperature, which really tells us, if you think about it, that if an object is good at absorbing radiation, it must also be good at emitting radiation. So what's really good at absorbing radiation? Well, a black body, right? Something that's just black, right? Black absorbs all frequencies, and so a black object is good at radiating things away. What's bad at absorbing radiation? Well, a mirror. Mirrors are terrible at absorbing radiation, so a mirrored surface must also be a very bad emitter. And sometimes after sort of marathons, you see the runners sort of with these silvered vests around them, or if you look at spacecraft, they tend to be silvered as well. The idea being that a silvered surface is very bad at emitting radiation, and it's a good way to insulate things. Wrap them in silver foil or a silvered surface. The silvered surface is very bad at radiating because it's also very bad at absorbing. The ultimate sort of example of this, I guess, is the thermos flask, insulated bottles. You have a vacuum between the hot part and the outside. The vacuum prevents conduction and convection, and then the inside will be silvered as well, and that prevents radiation. So in science we call it a Dewar flask. Thermos is a brand, though often people call them thermos flasks. But the vacuum bottles that everyone has these days, they cut down on all three heat transfer mechanisms by using a vacuum and a silvered surface. Okay, hang on, let's go back. If you're sitting in a place that is too cold, your body radiates more heat than it can produce. You'll start shivering and your metabolic rate will increase unless you put on warmer clothing. You sort of know that, right? This is someone in sunlight. How much radiation do you absorb? Well, we have this quantity here, which is sort of the solar radiation hitting the atmosphere. This is the direction of the sun. And so what we have to do, we have to make a cosine theta correction to this. This is just really what we talked about when we did Gauss's law and the flux. We need this cos theta because we have to consider this is the area, but this is a cos theta. This is the radiation instant on the person. The reason we have seasons isn't because the Earth is closer to the sun at some times of the year. It makes no sense otherwise. It will be summer all over the planet. The reason we have seasons is because that the Earth is inclined in its orbit, and at this point here in the orbit, you can see that the sun would be directly overhead at this point here, which would be called the Tropic of Cancer, and in the summer, the northern summer, the sun's rays are more direct on the northern part of the planet and more spread out on the southern part of the planet. You can see, imagine as the Earth twists on this axis here, this part would never see the sun. So we know it's always dark at the South Pole in our summer, whereas if you're here, imagine the Earth spinning on its axis, it would always be daylight. So if you end up doing the astronomy class with me, we'll discuss this a lot more, but basically we have these various points on the globe. This is the Tropic of Cancer, equal in the south is the Tropic of Capricorn, and then if at this latitude here, that would be called the Arctic Circle. If you live above there, you'd have perpetual daylight for at least one day of the year, and that's the Antarctic Circle down there. Okay. Thermography is when you take infrared images of bodies. Again, the textbook's very medically orientated, and if you have a cancer, the trouble with cancer is that it has a high metabolic rate. It grows and reproduces very fast, which means it produces heat. So you can actually see signs of tumors or infection by taking infrared images of people and seeing, that's a warm spot there. There's something going on. There's a lot of metabolism going on there. It's maybe a tumor or maybe it's an infection. Okay, that's the end of chapter 14. I don't think I'm going to go through the summary, and we'll finish there, and then we'll take a look at the worksheet. There's quite a few questions. Okay, so let's stop.